So in question number 1, we're not multiplying two polynomials by one another, we're adding one polynomial to the other. And because we're using a different operation, that means that different strategies, different properties apply to how we add one polynomial to another. So how did you approach number 1? What did you do? Or what did you add, maybe is another way to say it.
I add. I'm sorry.
Larry? All right.
I add exponents.
Add exponents. What does that look like? What's
3v to the 4th.
So you had a 3v squared coming from over here, you had a v squared coming from over here, and you turned them into this? Is that what everyone did? Is it? Larry?
I added 4v squared.
All right, so now is when we get to take a vote again. So let me get a quick show of hands for this problem. How many of you ended up with a 3v to the 4th as part of your answer? A couple of you. And 4v squared? All right, so the 4v squareds have outvoted you. Tell me about 4v squared. Why is it 4v squared? How did you decide that that's what was going on? Peter?
Because they have the same power, you don't change their power, you just combine the terms.
You combine the terms, right. And what is it that tells us in this problem that we can only combine the terms that have the same exponents, and we can't do anything with terms that have different exponents? What is it about this problem that makes that the case? Addition. Right. So rather than say add exponents, what I would say is what we really want to add is we want to add the like terms. That's really what addition of polynomials is all about. That's the engine that drives the addition of one polynomial with another polynomial. Because when you add expressions together, we can only combine them and make them simpler if the terms are the same. It's like the analogy I like to use is, let's say I want to add 300 and 400. I can add those together and get what? 700, right? I'm starting out with something that has a denomination of hundreds and adding it to something that has a denomination of hundreds, and their sum is something that has a denomination of hundreds. Right? So that's something that happens with like terms. We have something which was an x squared, we're adding it to something else which is an x squared, and the result is still something which is an x squared. Right? And the number of x squareds that we have is the same as the number of the first plus the number of the second. 3 of them plus 4 of them gives us 7 of them. On the other hand, if I tried to do something like add 300, which has denominations of hundreds, and add it to 40, am I going to get 7 of something? Well, no, right? I'm starting with things that have 2 different denominations. When I add 300 and I add 40 together, I don't get 7 of anything, right? 3 hundreds plus 4 tens is not 7 hundreds, and it's not 7 tens, it's not 7 thousands. So we can't combine those two together to make one single type of dollar bill or whatever, if you like, right? So we can only add across like terms, and when we do that, we add the coefficients of those like terms. One of the things that the other textbook, the textbook that we teach Math 090 out of, recommends doing is kind of arranging your polynomials when you're adding them or subtracting them in what they call a vertical format. And what they mean by that is to line up the like terms above one another. So 3v squared and v squared, line them up with one another. V squared minus 4v, I'll put the minus 4v under the minus 5v. And the plus 6 I'll put under the 2. So we're going to line up the terms that are like to one another in their columns. Because what they're setting us up to do is to make the analogy between adding these polynomials to one another and adding numbers in multi-digit arithmetic. Right? It's the same as if I were adding 352 plus 146. How do you add numbers with multiple digits in them? 352 plus 146. What do you end up actually adding? Yeah, you just add vertically. You add down the columns, and that's because we're adding here digits that have the same place value, the same denomination. The ones digits add together. I have 2 ones plus 6 ones is going to give me 8 ones. Likewise with the middle column, the tens digits. 5 tens plus 4 tens add together to give me 9 tens. And then the hundreds place finishes the calculation. So the usual addition algorithm that you learn how to apply for multi-digit numbers is the inspiration for the vertical method you can use to add 2 polynomials together. And the first step of it is the same in both cases. The step is line up the things that have the same value, the same place value in the case of numbers, and the same degree, the same exponent in the case of expressions. And then when it comes to doing the addition, we'll just add directly down the columns, just like we do with multi-digit numbers. So my constant term, negative 2 plus 6, is going to be 4, positive 4, so I'll put a plus here. Negative 5v plus negative 4v. Negative 9v. Right, again, because they're like terms, their coefficients combined, but the variable factor remains the same. They were v's to begin with, and they were v's after we added them. And 3v squared plus v squared. By the way, why is it 4? What's the coefficient of this v squared sitting here?
1.
Yeah. Don't neglect that little 1 there. If you don't see a coefficient in front of an expression, remember that that's a coefficient, a hidden coefficient of 1. So this is what our Math 090 authors of that textbook call the vertical method for adding polynomials. It's kind of slick, again, because of the analogy to how do you add multi-digit numbers. If it works for you, use it. If it doesn't work for you, then use what works for you. But I happen to think it's nifty. We can also apply it, as we'll see in a minute, to multiplication as well.